All right, level 3, line V1, we're going to take a look at DC deceleration, commonly referred to as braking. We've got two main types of braking that we can go and take a look at. We are going to go and have electrical, and we are going to go and have mechanical braking. Mechanical braking can stay after we go and power it off, so it's going to go stay on our system. Electrical is only going to be during the deceleration that we are going to go and have the electrical braking that we would see, or the electrical deceleration. As a result of that, there's going to be certain applications where we can use electrical fast stops on equipment that we would want to go and slow down really quickly for whatever reason. But it's not going to be for safety. No safety. Because for something to be safe, we would have to go and have braking that would be present at all times. Mechanical braking is going to allow us to do fast stops, but it's also going to go and stay on the safety. We can stay on the system, which is going to give us safety type of braking, particularly for things like cranes and hoists, elevators, stuff like that, that might have an aspect of it where people might be around these components. We would want to go and have mechanical braking that is going to go and be present. We're going to talk later on about plugging a motor to a stop once we start going into the AC, and plugging a motor would be where I reverse the power to a motor, which is going to go and cause that motor to come to a stop. If the motor is running it forward, I then run it into reverse, and it's going to go and cause this thing to stop relatively quickly. But if I keep maintaining that reverse, then it starts up and starts running again in reverse. That would be a form of electrical braking. It's not going to be covered inside of here, but it's a form of electrical braking that would then go and form a massive danger for our operators. We'll cover the dangers associated with that one when we actually get to our AC. For now, let's go and focus on the DC. First one that we're going to talk about is going to go and be electromechanical braking. And the picture that I'm showing you over here isn't inside of your binders, but it's going to go and be a DC compound motor, this is going to be a drum brake that is going to be attached or placed onto a motor itself. What we'll commonly have is we're going to go and have motors that are going to have an elongated shaft. So if this is my motor itself, I'm going to have a shaft that's going to come out of both ends of that motor. What I will do is I will go and have my load that is going to be attached to this one, whether through pulley, gear, whatever. And then on the far side of this, I'm going to go and have my braking mechanism so that I can handle my braking separately from my load. The way that these are physically put together is we're going to go and have a drum. That's going to be this section over here. The drum is going to be similar to drum brakes on a vehicle. Around the outside of the drum, I am then going to go and have two pads that are going to be on curved brake shoes. And the two pads are just going to be made with a type of material that is going to go and enhance braking without causing a lot of wear. Carbon types of materials generally seen for these ones. I see that both of these are fastened down on the very bottom over here. They're hinged down here on the bottom. And what I'm going to be able to do is I'm going to be able to go and take a solenoid over here. And there's a solenoid coil that's going to be around the outside of this thing. That's these windings over here. There's a spring here as well. And I'm going to be able to go and pull in, using this electrical solenoid, I'm going to be able to go and pull in the armature, the actuating rod. So this whole section moves in when I go and energize this solenoid. There's a spring that's trying to go and push it out, and as soon as I lose power to the solenoid coil, that spring would go and shove this back out. And as it would go and shove this back out, it would push this actuated rod in that direction, which would go and pull this brake shoe up against the drum itself, giving me mechanical braking. You'll note that the braking action actually happens happens when we power this thing off, rather than when we power it on. We power it on to free the motor, we power it off to brake the motor. And it's going to go and give us a fail-safe. We want this to go and happen like this so that the brake will automatically apply if I lose power. That way, if it's power that's been lost to the motor because I have pressed the stop button, that's fine, it's going to brake it. If it's power that's lost because a fuse has gone, or the mains have tripped, or the overloads have kicked, any reason that shuts off power to the motor is also going to go and release the braking solenoid, and then the spring just pulls that thing back out. Here's what that system itself actually looks like. Now, inside of here, there should be some components that are going to be relatively familiar for you. All of this, the stop, the start, the contact, the motor, the overload contacts, all of that is going to be part of my standard low voltage protection 3-wire type of circuit that I would go and use for control. What I see I've also got is that I've got this braking solenoid that is placed in parallel with my main motor coil. So that anytime that the main motor coil is going to go and be energized, I'm also going to be energizing the braking solenoid. Remember that the braking solenoid energizing is what releases the brakes. So anytime that I energize the coil, the brakes are going to go and be released. And for the rest, this thing operates the exact same as what we would have looked through in previous learning tasks. We press the start button. As soon as we press the start button over here, we complete that path for current flow. We would get current flow, my control current that would go and travel through here, up like that. At the same time as it travels through there, we're going to have current that's going to go and travel down and through my braking solenoid. It's going to enter to this junction. This is going to enter to that junction. And this is going to have closed and sealed in my contacts over there so that I can go and pull my hand off of that start button, and this thing is going to go and stay sealed in. You note that the braking solenoid and the motor are both going to be energized at this point. That goes and gives me current that can travel through my shunt field, as well as current that's going to be able to travel through my armature and through my series field. And when I get that current that is traveling through there, my motor is going to go and operate. As soon as I shut the motor down, I'm also going to de-energize that braking solenoid at the same time as I de-energize all the power to the motor. And this is going to go and apply, once again, that mechanical braking onto here. That's going to go and stop your motor. That's our electromechanical braking. The next one that we're going to talk about is something that's going to be called dynamic braking. And dynamic braking is going to be an electrical form of braking. And it's only going to be effective during the operation. Once the motor has stopped, it's not going to do anything. We're not going to see anything that's going to happen off of this thing continuously. Before we go into the drawings, the figure 2 and figure 3 that they show us over here, let's just go and talk real quick about dynamic braking, what it actually is. Let's talk about some drawings that we've had in previous ones. These drawings are not here. The figure drawings aren't even in the module, but the one down here is just from my motors, the very beginning learning task of motors over there, where it showed that we have got different types of things that are going to go and happen, different thrusts that we are going to get based upon whether something is a motor or whether something is a genset. Let's talk about this thing first as a motor, because that's how we would go and start this thing out. If I have this thing running as a motor, this over here is my right hand. Take a look, it's the right hand pointing towards you. We would be able to go and figure out what we would have for thrust. Remember, the thumb is the very last thing that we would go and take a look at. So what we would want to look at is we would want to look at first finger, which is going to be, first finger, which would be my flux, and center finger, which would be my current through the conductor. So if I were to go and turn this hand, just imagine now that you're looking at the back of the hand, and if I would have the first finger pointing across from north to south, and the center finger pointing in, I would see that on this side of the motor, my thumb, my thrust, would be showing me I'm going to go and create this sort of rotation. So my motor starts out, it goes and runs. Once the motor's up to full speed, if I would remove power from the motor, I'm still going to go and have centrifugal motion, right? We've got that armature and we've got the load spinning, so we're still going to have centrifugal motion, and it is going to be in the same direction, rotation. So I would still have rotation that would look like this. If, however, I take that rotation that is going around like this is centrifugal at this point. If I were to take that rotation that's going around and at the same time I were to go and re-energize just the field coils, okay, not the motor armature, but just the field coils, now I would have most of what I need to go and create any sort of a voltage, right? EG is equal to VLV. I've got flux density, I've got length of conductor, I've got velocity provided by this centrifugal force. All of that is going to allow me to turn this thing into a generator. And if I would connect a load across the armature, my DC machine would act as if it were a generator. So we'll get to connecting the load in a minute. Let's just take a look what would happen. If we would do that so, we would then have to go and use our left-hand rule. And if you take a look at the drawing that's shown over there, that is going to go and be a left-hand rule. It's just flipped upside down over here. But once again, center finger is going to go and be current. First finger is going to go and be field, and thumb is going to go and be my thrust that I'm going to go and have. We're going to go and take a look at this, just going across over here. We're going to examine the right-hand side over here. Imagine that this hand is once again turning so that you're seeing the back of the hand. That would be seeing this side of the hand over here. The first finger would point across in the direction of the field. The thumb would point in the direction of the thrust, which going down on this side is going down, right? And then the last thing that I would go and establish would be my current. I would see my current is going through in the opposite sort of direction, right? So this is going to go and give us now what we would get during a DC generator. I'm going to go and have current that is going to go through in the opposite direction over here. Well, how does this go and stop a motor? Well, it's going to stop if we take a look at what's happening around each of these individual conductors. Right over here, we're just going to examine this one over here, where we've got current heading in. So we've established that this rotation and a field across there is going to have current that's going to be heading in. So we reverse that direction of current. If I take a look at this and I use my left-hand rule, stick your thumb in the direction of current flow, stick your fingers around, you're going to see that this thing is going to go and rotate now in a counterclockwise manner. Once I see it rotating in a counterclockwise manner, I'm going to be able to go and see how it is going to go and interact with my norths and my souths. So these are my direction, my field rotating around here. Just make that a really clear arrowhead. I'm going to fire a line of flux through from here. When that line of flux catches into here, I'm going to see that it's going to get caught and ripped around like that. Well, if I take a look at this, which direction am I going and stretching this magnetic line of flux? I'm stretching it down. So it's going to go and give me a repulsive force that is going to try to go and fire this conductor back up and out of here. This is all going to be based upon, or the amount of braking is going to be based upon this other formula that you've seen, which is going to be that T is equal to K phi N, the amount of torque, or the amount of force I'm going to get off of this motor effect over here, where it's generated right now, but it's fighting back against it, is going to be based upon my speed. So the higher the speed, the higher the torque. But as my motor goes and spools down, as it fights against this and this breaks it, then it is going to go and have less and less torque. So the braking force is actually going to go and decrease as we get closer and closer to actually going and having the motor come to a standstill. All right, let's go talk about the circuits that are here. The circuit for this is going to be similar to our other ones as far as our 3-wire start is going to be, except now I'm going to go and have 2 contactors that are going to go and be inside of here. I'm going to have one that's going to be my dynamic braking one. I'm going to have one that's going to go and be my motor one. When I press my start button, I'm going to go and seal in through all of this. My DB, dynamic brake, is going to go and fire, which is going to go open this up over here. At the same time as it opens that up, it is going to go and close this one that is going to go and be over here. And as it closes that one, it is then going to go and fire that motor contactor coil. As I fire that motor contactor coil, these are going to go and close over here. And if I were to trace my paths for current through here, I would see that I'm going to go and have current that is going to go and travel through my shunt field winding continuously, F2 to F1. At the same time as I'm going to go and have current that is now going to go and travel through my armature. It's not going to go through that bottom rung because this is now sitting open over here. My motor is going to pick up, it's going to go and run, accelerate, we're going to do work, and then at some point we are going to go and hit stop. And when we go and hit stop, a couple of things are going to go and happen. I de-energize this one over here, which is then going to, as soon as that de-energizes, drop out this one over here, which is going to go and drop these ones out over here, which is going to go and interrupt this current over here. Note that the shunt field is still in the system. It's permanently attached over here. At the same time as my DB, my dynamic braking contactor, dropped out, it is going to go and reclose this over here. And what I'm going to have happen is I'm going to go and have my armature, which is going to go and reverse direction of current. That's going to go through. It's going to go and spin that current off, and it's going to go and dissipate that across a resistance that gets switched in here. We're using centrifugal motion to go and give us rotation on that armature. That centrifugal motion is giving us rotation. Because of that, we have got that EG is equal to BLV. We are generating a value of voltage, and because this has reclosed in down here, the dynamic braking contactor has reclosed in over there, now we've got a complete path for us to dissipate this. You should have been around a couple of generators in your lifetime. I don't know what your experience is in the electrical field, but even just camping or something like that. If somebody has got a small little job site generator, when we go and add load onto it, you'll hear that thing bog down. It's that motor action. inside of there that's bogging that thing down. In this case, we are giving it unrestricted motor action. We're just going and using this resistor over here to go and dissipate the watts so we can get them out of the circuit as fast as possible. But we are going to go and take all the voltage that we can generate off of this based upon the flux density, which we've got full flux density. That's going to be off of this and this. Over top of my full length, that's going to be the actual armature, and then it's just going to be going across a decreasing velocity because the velocity of this is going to be dropping because we are breaking that over there. It's a wonderful little thing, really, really simple to go and set up. I mean, all we really need is a little bit of resistance and a little bit of control components when we take a look at it. The only drawback to this system that they have over here, the DC shunt motor with the dynamic braking, is the fact that I'm constantly going to go and be burning power through this system over here, where I'm going to be running current through that shunt field. If we don't want to go and run it through the shunt fields, what we can do is we can add in a timing relay over here. And this timing relay is just placed in parallel with my dynamic braking one. This contact over here is going to go and be of the off delay type. Call this thing off delay, which means it is going to go and instantaneously operate. Remember, these things are going to go operate. Then there's going to go and be power off, operate to loss, ... and then they're going to change again. So we'll see this one over here. This is going to go and be a normally open time to open, NOTO, that we are going to have over there. When we first go and provide power to this, so we're going to go and provide power through the start button, through there. This is going to go and energize. This is going to go and energize. The instant that we energize it, it closes this contact over here. So this contact is going to stay closed. This is going to close. This is going to go and energize over here. These are going to close. These are going to close. And this has opened up because it was attached to that dynamic braking contact up top there. At this point, we would see that we would have complete paths for current. I'm going to have complete paths for current through here. That's going to be my armature current. And I'm going to go and have complete path for current through here. That's going to go and be my shunt field current that I'm going to have through there. When we go and press our stop button is going to go and cut out this circuit over here. This circuit is going to go and shut down. My dynamic braking is going to go and shut down. It's going to shut down this motor contactor over here, which is also going to shut down this over here, and it's going to go and reclose this. So instantly, I'm going to go and switch over using my centrifugal motion. This is still spinning around. I'm going to switch over and start dissipating current through this little resistive circuit over here. As I dissipate that current through that little resistive circuit over there, it's going to go and wind down because we have got this same EG is equal to BLV, right? My flux density, my length, and my velocity are all going to go and be inside there. I've got another one as well that's the same formula. You should be familiar with this one as well. It's equal to K, phi, and N. So it's going to be for a generator, my machine type, the flux that I have, and the speed. It's still the same thing that we're looking at for these. We're going to be looking at generating a value of voltage. This is going to go on, and this thing is going to go and lose its torque, because that's going to be a K phi N there as well, or K phi I that I have for that one, my apologies. But we're going to go and cause less and less braking action as it spools down, as it gets slower and slower, and eventually at some point we're going to run out. This thing might stay energized for a while, but because it's a normally open time to open, the second that we provided a drop in power to this, since we shut this off, that's when this thing started doing its timing. So the whole time while this is spooling down, this is still maintaining this closure, and at the end of its timing, boom, it's going to go and return back to its open, which is going to go and disconnect our shunt field. Because it does not go and provide uniform braking, it's not like an instant amount of braking, it's a relatively fast deceleration, but it is based upon the centrifugal force. There are going to be times where we do also throw on additional mechanical braking for these. Very last thing that this module talks about is going to be regenerative braking. And regen braking is where I'm going to go and take my current, and instead of going and burning it off through a load the way we are over here, what I'll do with that current is I'm going to go and take that current and I'm going to send it to something else external that is going to go and charge batteries. Okay, we'll just scratch this all out over here. All we would do is we would have a circuit that we would go and close in and we would divert it somewhere else so that we can go and drive it back into a system where we'll be able to go and utilize it later on. We don't lose all of those watts. Energy cannot be created or destroyed. It can only be changed form. So we can go and take it from kinetic, active energy, to potential energy. We can stick it back into a battery or something like that. Usually it's going to be on more expensive types of components. We'll use them on things like locomotive banks. We will use them on some large types of industry. Even electric vehicles do this, where instead of braking with dynamic and just burning it off as heat, they're going to go and stick it all back into the battery. This is all going to be done through solid state control semiconductors, which means it's going to be a lot more complicated. We're not going to go through the inside guts then, because once again, it's going to be an area you're not going to specialize in. It's just going to be something you're going to hook up, if anything, to some of these. So those are a completely separate type of subject. They're outside of the scope of what you need to learn here for level 3 electrical. So we'll leave it at that for them. If you do end up working on them in the fields, you're going to have full spec'd out prints from them, because they're a complicated, complex system, and we can't just be running current towards batteries and hoping for the best. We have to be real careful with it so we don't end up, blowing anything up, etc. All right, that is it for the DC machines here.